So class is being recorded. So let's start. So whoever is ready, I have Emma, Hao, Ikera, Jie, Tom, Xiuyun, Yinping, Yongxin. GS, yes.
This is question 22 for chapter 4. Suppose that two teams play a series of games that ends when one of them has won I games. Suppose that each game played is independently won by team A with probability P. Find the expected number of games that are played when part A I equal to 2 and part B I equal to 3. Also show in both cases that this number is maximized when P equal to 1/2. So for the given, we know the probability. So the A denotes the team A. The probability of team A wins is P, and the probability for team B wins would be 1 minus P. And the random variable be the number of games played. So for part A, when I equal to 2, we have two possible cases. So there's when 2 games played and when there's 3 games played. For the first one will be AA, that means team A wins and TA wins 2 times in 2 games. So we have those two, and then once we change the expression, we got P squared plus 1 minus P squared. Once we simplified it, we got this. And for when the x equal to 3, we have those 4 possible cases. And then once we simplified it, we got this. And the expected value will be 2 will be this one times this one, and then add this one times this one. So, and then once we plug in the P value, we can see when the P is 1/2, it reaches to the max value. And for the part B is similar, but there's more possible case. And at the end, we got this. And when the P is 1/2, we also got the max value.
Nice, you even have the picture.
And yeah, that will be it.
Great. Good job.
Thank you.
So you get a polynomial, downward quadratic, and also a polynomial degree 4. Great, good. So you can see everything ties together. Okay, that's J. Next one.
I'll go, if that's okay.
Sure.
Okay.
Oh, sorry, you could go. Go ahead.
Okay, thank you. So, Professor, I'm going to present question number 24 of chapter 3.
Okay.
The problem statement is that urn 1 contains 2 white and 4 red balls, whereas urn 2 contains 1 white and 1 red ball. A ball is randomly chosen from urn 1 and put into urn 2, and a ball is then randomly selected from urn 2. So we have to find what is the probability that the ball selected from urn 2 is white, then what is the conditional probability that the transferred ball was white given that a white ball is selected from on 2. So for part A, let's denote the events W for white and O for red. On 1 contains 2 white and 4 red balls. On 2 contains 1 white and 1 red. So we have possible two cases. Case 1 says if ball chosen from on 1 is white, then we have the probability is equal to 2 white over total balls, which are 6. Probability white ball from on 2. So we have choose one white ball from on 1 and put it into on 2. Then we have total ball 3 and the white are now 2. So probability will be 2 over 3 for on 2. Then we have the probability of white 1 and white 2 is equal to 2 over 6 multiply 2 over 3, which will be equal to 4 over 18. So this is our case 1. So the case 2 will be if ball chosen from urn 1 is red, because in urn 1 we have one ball is red and one is white. So for the red ball we have the probability for urn 1 is equal to 4 over 6. 4 are our red balls, this is red balls, and 6 is our total balls. Then the probability of white ball from urn 2 will be 1 over 3, because 1 is red and the second ball which we take from the urn 1 is red. So that's why 1 over 3 will be the probability for white ball. So then the probability of red 1 and white 2 ball is equal to 4 over 6, which is for this one, and multiply 1 over 3, which is this one, which will the result will be 4 over 18. Probability ball selected from on 2 is white, which will be equal to for the case 1 plus case 2 is equal to 4 over 9. Then we have to find the conditional probability. Probability transferred ball is white given by white ball is selected from on 2. The formula of conditional probability is written below. Probability transferred ball is white and white ball is from on 2 over probability white ball selected from on 2. So 4 over 18 we have find in these two cases, and we have to take the intersection of both cases. So we will get 4 over 18 over then the result of the summation of both two cases, 4 over 9, which will be equal to half, 0.5.
Great. Okay, that's a good review of chapter 3, conditional probability. Okay,
Yes,
nice.
Professor.
Thank you. Yeah.
Thank you.
Emma, you can go if you're ready.
Okay, thanks. Sorry, I lost internet, so it disconnected.
Oh,
Okay. Can you see?
yeah.
Okay. So I'm doing 4.13. So a man wants to buy tablets for his 2 daughters at Christmas as Christmas gifts. He goes to an electronics shop that has the 2 latest models. The probability that Sabrina, the older daughter, will accept the gift is 0.9, whereas the probability that Samantha, the younger daughter, will accept the gift is 0.7. These two probabilities are independent. There is a 0.8 probability that Sabrina will choose the first model, which costs $600, and a 0.2 probability that she will choose the second model, which costs $450. Samantha is equally likely, so 0.5 and 0.5, to opt for either model. Determine the expected total cost that will be incurred by the man. So at first I was really confused because I wrote S's and they're both start with the S. So I rewrote it. So model 1 is 600 and model 2 is 450. So the probability that Sabrina will accept model 1 and model 2 is here as 0.8 and 0.2. So I multiplied that by the cost of each of the models. So that got me $570. Then I looked at Samantha. So the probability that she will accept what she's given, which here it says is equally likely. So I multiplied 0.5 by both of the prices of the models to get 525. Then the probability that they will accept the gift, so that they will actually take it, is 0.7 and 0.9 as here. So then I multiplied their cost of their probability of accepting their own personal model to accept what they're given by each other, and then I added them since it's one man buying both of their gifts. So that got me $880.50.
Great. This is a very interesting question, huh?
Yeah, I liked it. It was the S's that got me confused at first, so I'm glad I got it.
Very nice. Thank you.
I'm doing question 4.21.
Okay.
Both buses carrying 148 students from the same school arrive at a football stadium. The buses carry respectively 40, 33, 25, and 50 students. One of the students is randomly selected. Let X denote the numbers of students who were on the bus carrying. The random selected students. One of the 4 bus drivers is also randomly selected. Let Y be the numbers of the students on her bus. Expected value of X will be like larger since like the expected value of Y is equally likely amount. And for B, I just write down like this one, x1 P of x1 times plus x2 and P of Px of x2, and then add it up to get 39.28. And expected volume for Y is 40 times 1/4 since they were like 4 bus drivers plus 33 times 1/4 and 25 times 1/4 plus 50 times 1/4, I got 37 for Y.
Okay, so why A is 50? Why does so A you're saying they're the same?
No, the X will be like bigger, larger for the
Right. That's through B, right? Your answer through
yeah.
B.
Here's
Okay,
the
so
answer to B.
A basically just guessing, right?
Yeah, just guessing.
Okay, I see. I see. So through the calculation, then you said, okay, expected value of X would be larger, right? Because you calculated it here. Yeah. Okay. Yeah. Good. Good. Okay, who's next one? So Emma, Hai, Kira, Jed. I have Tom, Shoyin, Yinping, Yongxin. Who wants to go first? So 4 of you.
I can go first.
Okay.
I'm doing question 20. A gambling book recommends the following winning strategy for the game of roulette. Bet $1 on red. If red appears, which has the probability 18/38, then take the $1 profit and quit. If red does not appear and you lose this bet, which has the probability 20/38 of occurring, make additional $1 bet on red on each of the next 2 spins for the roulette wheel, then quit. Let X denote your winning when you quit. A. Find Px greater than 0. So Px greater than 0 is the probability that you win on the first spin plus the probability that you lose and the probability that you win the next 2 spins. So by the given information, the probability of you winning on the first spin is 18/38, and the probability that you lose is 20/38. So the probability of X greater than 0 is 18 over 38 plus 20 over 38 times 18 over 38 times 18 over 38, which is 0.5918. And B, are you conceived that the strategy is indeed a winning strategy? Explain your answer. No, because from the given information, the probability of red appearing is 18 over 38, which is less than 50% chance of winning. So no, I'm not convinced that this is a winning strategy. C, find E of x. P of x equals 1 is solved in part A, which is 0.5918, and then P of x equals -1, which is 0.2624, and then P of x equals -3, which is you losing all three, which is 0.14578. So E of x is 1 times 0.5918 plus -1 times 0.2624 plus -3 times 0.1458, which is -0.108. So you're expecting to lose around 10 cents every time you play.
Yeah, nice. Yeah, so people use this for games. All right. Nice. So this is a typical example of that. Thank you.
Thank
So that's Yongxin.
Good evening, Professor.
Good evening.
Can you see
Show
my
you.
Can
Yeah.
you- Okay. So I'm going to present question number 19 from chapter 4. So if the distribution function of the random variable x is given by fx equal to 0 if x less than 1, and 1/4 if x is between 1 and 3, and 5/8 if x is between 3 and 4, and 3/4 if x is between 4 and 6, 7/8 if x is between 6 and 7, and 1 if x is greater and equal to 7. So the question is calculate the probability mass function of x. So in here, I draw a graph that we can easy to see. So the probability mass function of x that we want to calculate is between the each two variables. So in here, the probability of x equal to 1, which is between the 1/4 and 0. So it's 1/4 minus 0, which is equal to 1/4. Then the probability of x equal to 3 is between the 5/8 and the 1/4. So it's 5/8 minus 1/4 is equal to 3/8, and the probability of x equal to 4 is between the 3/4 and the 5/8. So it's 3/4 minus 5/8, which is 1/8. And the probability of x equal to 6 is between the 7/8 and the 3/4. So it's 7/8 minus 3/4, which is 1/8. And the probability of x equal to 7 is between 1 and the 7/8. So it's 1 minus 7/8 is equal to 1/8. So the answer is like that.
Great. Your adds up to be 1.
Mm-hmm.
It's very clear. Okay, thank you.
Mm-hmm.
Okay, Tom.
Hi, yeah.
Nice. I see your work is neater than before.
Thanks. So we're given a number from 1 to 10 that's randomly chosen, and we have to ask, is it I, where I is equal to 1 to 10? So for each question we ask, like, is it 1? And then they'll say no, for example. And then we'll ask, if is it 2? Then they might say no, and we repeat this process until we get yes. Is it 7, for example? So it's a this problem is the expectation of a random variable where x is the number of questions asked if x is equal to xi for xi is equal to 1 to 10. So for the expectation of xi, we have the sum of xi times the probability mass, which is p of xi. And so for the expectation of x, since each number is from 1 to 10, we can factor out the 1/10 and then multiply that by the xi value, which is 1 plus 2 up to 10. So we get 55 divided by 10 is equal to 5.5 questions asked as our expected value of x. So that's for part A. Part B is, with each question, try to eliminate 1/2 of the remaining numbers. So for this one, this is like a binary search. It's a pretty common algorithm in computer science where you ask if it's the less than the middle value. So for example, if you start with 10 digits, you would ask, is it less than 5? And that gives us 2 possibilities, from 1 to 5 or 6 to 10, depending on whether they say yes or no. And we repeat this process of asking, is it less than the middle value, until we get just one possibility left. So for the expectation of x, where x is the number of questions asked, we have xi is equal to 3 or 4 questions, because the depth of this tree is either 3 or 4 levels as the maximum questions you would ask. So in this case, we have xi is equal to only 3 or 4. So after you plug in, did it cut down? Okay. So e of x equals to the sum of xi multiplied by the p of xi again. So to get the probability of xi, we count the number of one element arrays, divide by the total number of one element arrays. And so we have 10 arrays that are just one element. And that's how you get the total number. And so we get 3 times 6 over 10 plus 4 times 4 over 10, which equals to 3.4 questions asked as our expected value.
Interesting. You always choose the very interesting questions. Very nice. Yeah. Anyone has any questions? All right. Thank you, Tom. Oh, sure, Catherine. Let me make a presenter. I think 音频, well, we still have 音频 and 永新. But Catherine, I'll make you present as well.
I presented already, Professor.
Oh, sorry. Okay. The only 音频 by showing has done already. 音频, did you do it? 音频 and Catherine. Oh, okay, it's popping up.
Okay, can you see my screen?
Yeah.
My question is, a teacher selects a group of 5 students at random from her class consisting of 11 female students and 10 male students. Find the expected number of female students in the group. That X denote the numbers of female students in the group, and for px equal 1 is choose 1 from the 11 female and choose 10 from the 4 choose 4 from the 10 male, and the total is choose 5 from the 21 students. So the answer is 100 and 110 over 969, and for x equal to is equal 200 and 2200 and 6783, and for x equal 3 it's 825 over 2261, and for x equal 4 is 1100 over 6783, and for x equal 5 is 22 over 969. So for the expected number, it just 1 times the answer, and 2 times the answer, 3 times the answer, 4 times the answer, and 5 times the answer, and the final answer is 55 over 21.
All right. Okay, thank you. Okay, Catherine.
Hi, Professor. Can you
Hello.
see? Okay.
Yes.
So I'm presenting 41. On a multiple choice test with 3 possible answers for each of the 8 questions. What is the probability that a student who has not studied for the test will get at least 6 correct answers? So, so since there's 3 possible answers for each of the 8 questions, like you will choose a probability of like 1/3. One of the answer will be correct, and then choosing the other 2 answers is 2 over 3. And then since we have to get 6 questions right among the 8 questions, to choose is 8 choose 6, and the others because we're saying at least 6 correct answers, if we get 7 correct answers, it'll be 8 choose 7, and then get all questions right is 8 choose 8. So the probability of 6, at least 6 correct answers is equal to probability of x equals 6 plus probability that x equals 7 plus probability of x equals to 8, which in here we get 8 to 6 times 1/3 to the 6th power times 2/3 to the 2nd power plus 8 to 7 times 1/3 to the 7th power times 2/3 to the 1st power plus 8 to 8 times 1/3 to the 8th power times 2/3 to the 0th power, which give us 112 over 6561 plus 16 over 6561 plus 1 over 6561, which give us the probability of choosing guess at least 6 correct answers is 43 over 2187.
So it's about 2%.
Yeah.
Okay. Very nice. Thank you. All right. Anyone else like to present today? Okay. Yeah. Let me make a presenter. Okay, you can go ahead.
Okay, give me a second.
Okay.
Screen. Okay, the question is, during a tournament, a football team plays a match against 3 different teams. The probabilities that this team wins against the first, second, and third teams are 80%, 65%, and 30%, respectively, and are independent. Let X denote the number of wins obtained. Calculate the probability mass function of X. Okay, there are 4 possible values of X. It's a 0, 1, 2, or 3. So it's a 0 wins, 1 win, 2 wins, and 3 wins. Let's A be the first team, B be the second team, and C be third team. Okay, that's what is given. Okay. Events of winning a game with any of these 3 teams are independent. And that's why the probability of happening 3 events, it's a multiplication of separate probabilities, of 3 probabilities.
So this means in words, what does
events are independent. That's why.
Oh, I see.
Like, yeah, I just calculate multiplying. Okay, so probability of not winning at all. That's a multiplication of probabilities of losing to the first team, multiplied by probability of losing to the second team, and multiplied by probability of losing to the third team. That's 1 minus 80%, 1 minus 65%, and 1 minus 30%. So the probability is almost 5%. The same way I calculate the probability of X equal to 1. It means 1 win after 3 games. That's a sum of it's a summation of 3 multiplication. First event when the team win the first team, lose to the second game and lose the third game. The second event plus the probability of the second event when the team lose the first game, win the second game, and lose the third game. And the third event is when the team lose the first, lose the second, and win the third. So this probability equal to 30, almost 31%. Okay, probability of X equal to 1 to 2 means 2 games. So that's again the sum of 3 multiplications. First event is the team who wins the first game, the second game, and loses the third one. The second one is it's losing the first game and wins the second and third. And last one is winning the first, losing the second, and winning the third. So their probability equals to 49%.
Wow, almost 50%.
Yeah. Okay. And probability of X equal to 3. There is only one combination when the team wins all 3 games. It equals to 16%.
Interesting.
And I checked if the summation of these probabilities equals to 1. Yes, it equals to 1. Yeah, it does.
Great. So it doesn't make a mass function. Great. And yeah, we can see why this P. So probability X equals when the random variable equals 2. So 2 winnings. This all depends on this 80% about the probabilities given. Interesting question. Interesting. Thank you, Ayat.
Mhm.
Anyone else like to present? Yes, you guys are awesome. Great. Okay, so what I'm going to talk about, let's see. I think I'm supposed to talk about variance. Okay, let's just read along. I think this is shorter section, variance. Is it? Then the Bernoulli and the binomial random variables. Okay, let's go through the variance first. So again, let's read together. Okay, this book is new to you as new to me. So given a random variable x along with its distribution function f, capital letter F, it would be extremely useful if we were able to summarize the essential properties of f by certain suitably defined measures. One such measure would be expected value of x. However, although expected value of x yields the weighted average of the possible values of x, it does not tell us anything about the variation or spread of these values. For instance, although random variables w, y, z having probability mass function determined as so, this is just one example, right? W equals 0 with a probability of 1. Y equals -1 with a probability of half, positive 1/2, z -100 with a probability of half, positive 100 half. So all have the same expectation. Namely 0, there is much greater spread in the possible values of y than in those of w. Right, so we see 0, -1, positive 1, -100, positive 100. And in the possible values of z than in those of y, because we expect x to take on values around its mean. Right, a lot of times we can treat expected value as mean. It would appear that a reasonable way of measuring the possible variation of x would be to look how far apart x would be from its mean. So let's measure the spread. On the average, one possible way to measure the variation would be to consider the quantity expected value of absolute value of the random variable x subtract this mu, where mu equals to expected value. Interesting, huh? So this is expected value of the random variable subtract the expected value. However, it turns out to be mathematically inconvenient to deal with this quantity. So a more tractable quantity is usually considered, namely the expectation of the square of the difference between x and its mean. It's very similar when we talk about normal distributions. We thus have the following definition, right? When we talk about normal distributions, before in the elementary statistics, we also have variances. So this is similar. So the idea is the same. So we take a square. So definition. If x is a random variable with mean mu, then the variance of x denoted by variance of x equals to expected value of x minus mean squared. Right. The random variable minus the mean squared. So we can see this variance definition is similar from before. So let's see how do we derive that. So variance of x is equals to expected value of x minus mu minus mean square. Then, by definition, expected value is defined as a summation of all those x values of the random variable, the square multiplied by its probability. The square, so perfect square can be expanded like this. Then we can split, so we get x squared times probability to mu, because mu can treat it mean supposed to be given. We have this x multiplied by its probability. Then we have this mu square, then all the probability. So we know this one equals to 1 times mu squared, because if it's a probability dense function, it has to add up to be 1. So sum of this probability for all random variable x, that's 1, so we get mu squared. And this one, what's this one? This is also mu, right? Expected value. This is expected value of x, little x, so which we call mu here. So 2 mu times mu, that's 2 mu squared. Then this one is x squared, and before we calculated once. So expected value of random variable squared. So negative 2 mu squared plus mu squared, that's just negative mu squared. So miraculously, we get this formula. So variance of the random variable equals to expected value of the random variable square subtract expected value squared. Very interesting, huh? Mathematics is just, you know, miracles. Sometimes, okay, anyway. This is amazing, isn't it? Okay, in words, the variance of x is equal to the expected value of x squared, the random variable square, random variable value square, minus the square of its expected value. In practice, this formula frequently offers the easiest way to compute variance of x. So variance is the same as before, just, you know, to check how the distribution, you know, how wide or how close they are. Let's see example 5.8. So we want to calculate the variance of x if x represents the outcome when a fair die is rolled. A fair die means has side 1 up to 6. So back to example 3a, we have calculated expected value for rolling a die to be 7/2. Now we just use that. So we want to calculate expected value of the random value square. So 1 squared times 1/6. Basically, we'll have 1/6 times 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. So adds up all those squares, we get 91 times 1/6. Then we square this. If we square this, we get 49/4. Then we subtract. So 91/6 subtract 49/4. Do some calculation, we get 35/12. Okay, what does this say? So this value is very close to 3. So because variance equals to this is the sum of non-negative terms, it follows that variance always non-negative, or means the expected value of the random value square is always greater than or equal to the expected value square. So in this case, we say this is a 91/6, right? It's greater than expected value square, greater, because we get a positive number, get 35/12. So that is the expected value of the square of the random variable is at least as large as the square of its expected value. All right, simple calculation. Anyone has any questions? Let's see this. 5b. The friendship paradox is often expressed as saying that on average your friends have more friends than you do. More formally, suppose that there are n people in a certain population, labeled 1 up to n, and that certain pairs of those individuals are friends. This friendship network can be graphically represented by having a circle for each person, and then having a line between circles to indicate that those people are friends. For instance, this figure indicates that there are 4 people in the community, and that person 1 and 2 are friends, 1 and 2 are friends, and 2 and 4 are friends, and 1 and 4 are friends, and 1 and 3 are friends. Let f of I denote the number of friends of person I. So let's see, person 1 has 3 friends, 2, 4, 3. So she's popular. Everyone is her friends. 3 is a loner, only has 1 friend, which is 1. So anyway, f of I denotes the number of friends of a person I. And let f be, so this f be the summation of all those fi's. Thus, for the network of this, 1 has 3 friends, 2 has 2 friends, 3 has 1 friend, 4 has 2 friends. So add together, this f equals the 8. So now let X be a random chosen individual, equally likely to be any of 1 up to n people. That is, probability of X equals I equals 1 over n. I goes from 1 up to n. Let it gi equals fi in proposition 4.1. It follows that expected value of f of xi, the expected number of friends of x, is sum of all these little fi's multiplied by the probability when the random variable is I. And because probability of x equals I is 1 out of n, so this is f of I divided by n. And what is the summation of fi from 1 up to n? And that one we call f. So expected value of f of x is the sum of all those fi's divided by n. Also, g of I is defined as f squared of I. It follows that expected value of f squared of x. The expected value of the square of the number of friends of x is this. Expected value of square of the f is f squared times the probability. Again, the probability of x equals to I is 1 over n. So that's f squared of I divided by n. And so the quotient of this expected value of f squared of x divided by expected value of f, well, this bottom just f, and the top is this, is anyway, well, that's a formula for, okay, anyway. Now suppose that each of the individuals writes the names of all their friends, with each name written on a separate sheet of paper. Thus, an individual with k friends will use k separate sheets. Because person I has f of I friends, they will be f equals the summation of all fi's separate sheets of paper, with each sheet containing one of the n names. Now choose one of these sheets at random, and let y denote the name on the sheet. Let us compute, okay, expected value of f in terms of y. So the random variable is y now. And what's the possible values of y? It's all these fi's, right? I goes from 1 to n. Now, because person I has f of I friends, it follows that I is the name on f of I of the sheets. And thus, I is the name on the chosen sheet with the probability of this f of I divided by f. Remember, f in the denominator is the summation of all, so it's that is probability of y equals to I equals to f of I divided by f. Consequently, expected value of this equals to f of I times probability of y equals to I. Right, probability of y equals to I is the same. It's this. It's f of I divided by f. So f of I times f of I divided by f would be f of I squared divided by f. Then we could see expected value of f of y equals to the numerator, because we can split this, the numerator is the sum of all those f squared I, which is this. Well, this will have divided, right? And then this one is f, right? This one is this guy. It's this f, summation of this f, which we say is greater than or equal to expected value of f of x. So this is like a proof of the statement before, where the inequality follows because the expected value of the square of any random variable is always at least as large as the square of its expectation. Thus, expected value of f of x is less than or equal to expected value of f of y. Which says that the average number of friends that a randomly chosen individual has is less than the average number of friends of a randomly chosen friend. This is tongue twisting. Let's see the remark. The intuitive reason for the friendship paradox is that X is equally likely to be any of the n individuals. On the other hand, Y is chosen with a probability proportional to its number of friends. Right, you see expected value of Y is this. Right? That is, the more friends an individual has, the more likely that individual will be Y. So Y is biased towards individuals with a large number of friends, and so it is not surprising that the average number of friends that Y has is larger than the average number of friends that X has. All right. So 5C is the example illustrating the usefulness of the inequality that expected value of a square. Expected value of a square is at least as large as the square of the expected value. So let's see this example. This should be practical. Suppose there are m days in a year, and that each person is independently born on day R with the probability of PR. So R equals to 1 up to m, because a year has m days. So summation of all those probability has to be 1. So let Aij be the event that the persons I and J are born on the same day. So now A, we want to find out probability of A13. So person 1 and the person 3. Hold on. Yeah. So person 1 and 3 have the same birthday. So what is the probability person 1 and person 3 have the same birthday? The probability of given the first person and second person have the same birthday, what's the probability of the first person and the third person also have the same birthday? And the third C show that this conditional probability is greater than or equal to, or at least, right? At least probability of person 1 and 3 born on the same day. C is interesting, huh? C is kind of anti-intuitive. Okay, let's see. Because even 1 and 3 have the same birthday is the unit of the m mutually exclusive events that they were both born on day R, and R could be any of these m days in a year. So we have this. We have probability of the first person and third person born on the same day equals to the summation of those probabilities squared for R. R can be, so R goes from 1 up to m days. Right? So basically probability of 1 and 3 on the same day. So those are independent events. So that's a probability of the first person on the day times the probability of the third person on the day. And the day could be any day of m days in a year. So we have this equation. B, using the definition of conditional probability, we obtain that given the first person, we know the first person and second person born on the same day. So what is the probability the first person and the third person also have the birthday on the same day? So that's probability. So the numerator is a probability of the first one and the second one have the same birthday, and the first one and the other one the same day. This is a formula from before, right? From conditional probability, defined by the temporary sample space, which is the probability of the first person and second person born on the same day, which equals to the numerator is n probability of that. So what is that? That is basically the probability of 3 people, 1, 2, 3, the 3 person born on the same day, right? Born on the same day. So probability for each is PR. R represents any day for m days in a year. So the PR times PR times PR, which is a PR cube. Then divided by the bottom probability of first person, second person born on the same day, which is PR times PR, which is P squared. Then this actually can be simplified if we want to do that, all right? Because we do have formula for P cube, summation of a variable to cube to third power, and also a summation of a variable to second power. So where the preceding use A12, A13 is a unit of the m mutually exclusive events that 1, 2, 3 were all born on the same day. For any day, R equals to m up to 1 up to m days in a year. All right, anyone else has any questions? C, it follows that from part A and B. So this is greater than or equal to this, right? because this one has to be divided by PR squared. It's equivalent to this one, PR cube, summation of this PR cube, which is now equal to summation of this PR squared, then square this. All right, because this one we want to show that. So to prove this inequality, we want X to be random variable that's equal to PR with probability of PR, that is. Then expected values we want to calculate. Expected value of this equals to times the probability, which this one, so probability, what is the probability of X equal to PR? Then simplify this. So it's just PR times PR squared. Then we calculate it with the random variable square. We get a PR squared times the probability of this, well, probability of this, sum of the probability of this. So just PR. So well, PR squared times PR, which is PR cube. Now, expected value of X squared is this guy, is at least is greater than or equal to, well, what if we square this? We square this square. Actually, I don't see that right away. Anybody see that right away for this inequality? So this is PR cube. Oh, hold on. Oh, okay, it is obvious, right? Because each little PR is less than 1. Yeah, if it's greater than 1, or if we don't know if it's greater than 1 or less than 1, we don't know. But because this each one is from 0 to 1, at most 1, let's put that. So this inequality works. Okay, I is giving support 0.2 times 0.2 greater than 0.2 times 0.2 times 0.2, right? Same argument as I was mentioned, yes. Because each one is less than or equal to 1, at most 1, from 0 to 1. That's why this inequality works. But if we don't know, because this is probability, right? Because each of these PRs is at the most 1. That's why this is true. Let's see. A useful identity is if A and B are some constant, so variance of AX plus B equals to A squared times variance of X. Interesting. B is ignored. To prove this inequality, let's see, let mu be the expected value of X. A note from that expected value of this would be this. Therefore, the variance we use the definition would be this one minus A mu plus B becomes minus A mu minus B. Then we calculate this. So this is the whole thing square. Plus B minus B is gone. Oh, that's why B doesn't contribute anything to it. Right? So then this one becomes AX minus A mu. So factor out A. So that's X minus mu square, factor out A square. Okay, that's why it's true. Cool. Okay, similarly we define something called a standard deviation of X. So standard deviation of X is the square root of the variance of X. All right, and Should we talk about Bernoulli and the binomial random variable? I'm going to leave for next time. If you could, you have time, you can go ahead of me, read this, Bernoulli and binomial random variables. Binomial, probably you know, Bernoulli probably is totally new to you. All right, I'm feeling tired. I'm going to leave this for next class. Anyone has any questions? Again, for those of you okay, for the rest of you, I want to show you this. I want to show you something. I want to show you this presentation grades. 50, 20, 0, 0, 0. You know, some people I just don't see them. Those two people, I haven't seen them for a while. I'm going to send them emails again to see what's going on in their lives. The 50, 20%, and I have reached 100% already, but keep going, okay? Keep going is you're going to be your extra points, extra credit. And some people have, Catherine has 90, just keep going. Tom has 80, then 70. All right, so my point is, Hal has 80. My point is, try to present, all right? Try to present. I like when you present. All right. Okay, so please prepare yourself to present for next class. If you haven't done much, if you haven't reached 100%, you know, above 100% is going to be your extra credits. Okay.
Professor, I got a question.
Yes.
Like, how will you like calculate the extra credits for the presentation?
So presentation, okay, that's a good question. Let's go here. Let's go here. But also, once you reach 100%, I'm going to be a little bit critical on your presentation. Let's go to syllabus. So the syllabus is the same as the grading policy right here. 15% attendance, 20% homework, 15% class presentation, right? So I'm going to, so there's 10 times. So once you reach 10 times, it's 100%. You already get 15% of your grades already. If you do extra, I'm going to give you the same weight. So basically you get a 1.5 points for each. All right, add to your final grades, because this is 15% is your final grades. So I'm going to just keep counting that. But again, as I said, I'll be a little bit critical on that. You cannot just choose a basic question to do it. You probably want to choose some interesting questions to show. If you present two questions at the same time, does it count as one or two presentations? Catherine, that's not a good idea. We still have time. So we are on the first 1/3 of this semester. We still have time. Ideally, you choose to present every class, right? Not to present two questions in one class. Yeah, you see some questions that have 1, 2, 3 parts. That is considered as one presentation. So this also gives me idea, you know, for advanced class, maybe presentation should deserve some more, deserve some more credits. Okay, anyone has any questions? If not, you're free bird for today. And go ahead and do your homework or prepare for your presentation for next class. Weight each additional presented question equals 1.5 points to the course grade. You're right. You're right. Can you see this? Let me make this larger. You see, this is grading policy. 15% attendance, 20% homework, 15%. So 15% 10 times, right? That means each one is 1.5. So this is counted to your final grades. This, yeah, 20% midterm, 30% final. Or maybe we should talk about midterm. So I'm thinking midterm, you know, what should happen in March. So one of my class just had midterm, and my other two classes will have midterm on 15th. So for this class, I'm thinking on March 22nd. Right, March 22nd, which means 2 weeks later. So I should post. So is it okay if we meet him on March 22nd? Yongxin, question?
Yeah, the 22nd is a Wednesday. We don't have class.
Oh, I was talking about for right, which means 21st. Right, for our class, because today's Tuesday, 21st. Because my other two classes falls on March 15, which is Wednesday. For our class, the 21st. 21st, let me make a note here. So is it okay for everybody? All right, let's set the date. So that would be midterm date. Then what else? So let's talk about, so then what's going to be covered in the midterm? So what we having, so 8 chapters. By the time yeah, we're going to cover the chapter 4 then, first 4 chapters. So, right, I'm going to make an announcement on this, all right? Okay, guys, any questions? If no, you're free bird for tonight. If you have questions, I'm here. I'm happy to talk to you about it. Thank you. Thank you. Have a good night. Okay, I have so many questions for the department chair. Tom? Oh. Okay.